Alright, hello everybody. As Nick said, we had a bit of a late start there because I forgot to make the tea, but it's Nick's fault. I was talking to him. He delayed me. He distracted me. How is everyone this week? Oh, made it up to 42 viewers. Panicking? Don't panic. You've got plenty of time, don't worry. Not everything will be obvious straight away, as I usually say. Work on it a bit. When you get stuck, come and talk to us. We'll help you through that bit, and then you move on to the next bit. I mean, obviously, you can't really control whether you panic or not, but the panicking doesn't help. Did I bump up the saturation even more? I'll have to... Yeah. Let's go to... so I'll drop the saturation. That look a little bit more natural? I guess most of you haven't seen me in real life. I could be that saturated, really. I'm just generally a bright, slightly overly red looking person. So I'll have to go through the filters and find something really annoying for next time. Okay, so it looks like we've got probably everyone who's going to come in. So the important thing while we're just waiting for a few stragglers to turn up is the tea. So what votes have we got this week? Don't need the t-shirt there. So we've got a pretty strong showing for Sydney breakfast. 1 for Russian Caravan, 2 for Earl Grey, 1 for Sencha, Matcha, Melbourne breakfast, so 3 for Russian Caravan. Yeah, I mean, I do quite like a Russian Caravan in the afternoon. The smoky flavour and aroma is quite nice. But this week we have, I mean, it is a black tea, so that bit's right. Still haven't got the tea cam yet. A quite surprisingly dark one. I think I left it in the thing too long. But it is Melbourne breakfast. That's not what I wanted. Wrong bit. I want that one. There we go. So it's now recorded for, well, at least as long as Ed exists. You can go back and check what the tea guess was this week. Okay. So let's talk about something. So this week... Oh, no, wait. I haven't actually started the recording, have I? Bad lecturer. Alright, so the usual one. Welcome everyone to, where are we up to? Week 8 of Programming Fundamentals for Autumn 2021. Technically the 3rd calendar year of the plague. Still only a year and a bit into it though, so we're doing alright. Haven't seen the Grim Reaper exactly stalking the streets yet. So we've spent a bit of time working with classes and objects now, and everyone's like, you're still in the, not even the middle, really, you're still at the start of understanding how objects and classes work, but that conception is forming, right? You've got some idea that there is a thing called a class, which is a definition for how to construct objects, but also serves this dual purpose of being a repository for information that all objects of that type should share. So that's what static stuff is. And in a way, you can think of it being a definition is sort of being a repository for information that all things of that type share, because they all share the same definition. So there's kind of a lot of things going on, but in a way that it's relatively unified. Where are you? And you have this idea of objects as instances of a class which store data that is particular to those objects. So the class says what data that they should store, and the objects are the ones that actually have the concrete values for that particular instance in it. And you can have lots of different objects of the same class, and they can all have different data, apart from anything they share that's on the class. In terms of types, because the class provides the structure for what an object is, it is both in theory and in practice the type of the object. Okay. So classes provide not only the practical definition of how an object should work, but they provide the concrete type information that allows the programming language to recognize, at least to some degree, whether you're doing the right thing. And also allows you to make certain distinctions about stuff. I can draw a picture. I don't know if it's going to be pretty. So, how am I going to draw this? That's a good question. So you have the class, and this is in some sense unique. There is, under a given name, there is exactly one class. And it's used to create lots of objects. Right. So all the objects are of the same type because they come from that class, which is the thing that gives it its type. But they all have different data, so they're all in and of themselves unique instantiations of the single unique class. So you can maybe think about why we do this. I mean, some of you who've been programming before will have probably a pretty good idea of this. And you can see some immediate advantages. Like, so if you want to create lots of, as we've been doing in the labs, lots of students or bank accounts or something like that, it makes sense to have an object which defines what it means to be a bank account. So what data should it store, what actions, i.e. methods, is it able to take, and have sort of that one coherent unified definition and be able to just say, okay, give me a new bank account. And then you automatically get all those things that are related to what a bank account is. But most of you won't know this, of course, but if you ever programmed in a different kind of programming language, so for example C, which is a procedural language, it's not an object-oriented programming language, there are other ways of doing this. Right? Just being a collection, like a unified collection of data and methods, is sort of the most basic and most boring part about having objects, and is not really the point of having them. So in C, you can quite happily have a thing called a struct, which collects together bits of data. So you can say this is, the struct for bank account has an int, which is the account number, and a string, which is the account name, and a suitable representation of how much currency it has in it. So neither double nor integer is a good answer for that, but it collects all that data together. It doesn't have methods attached to it in C, but you can define functions and just stick them in the same file that you defined the struct in, and have those functions do the work of the methods. You don't get you don't get some of the fancier stuff that we've seen in this, with like the privacy and things like that, and the type checking in C is a little different to how it is it's pretty close to what it is in Java, but not completely identical. There's a lot of implicit type coercion, so it's not as rigid as it is in Java. So C basically assumes everything is ultimately an int. So you can still kind of do that same job that we're doing at the moment with objects. So at the moment, all we're using objects for is as a coherent repository of data and methods. So that I can say, I want a new bank account, without having to say, well, actually what I want is an int for an account number, a string for the name, and a double for the balance, or however we're encoding it. So in the labs, doing it as a double, I think, or a float. And all we have to do is write one line. We don't have to write those 3 or 4 or 50, depending on how much stuff there is. And we don't have to some degree, we kind of don't have to guess which functions apply to our object, because the object comes with the functions that work on it, mostly. Okay. So there is that aspect of convenience, but that seems like not enough convenience to identify this whole new idea of an object-oriented programming language, as opposed to a procedural one, or even a functional one with good type definitions and stuff like that. So after that long-winded introduction, we get to what I mainly want to talk about this week, which is object-oriented programming. What are the basic ideas, and what is the point of it? Okay. Because one of the problems with learning something like Java or C++ is that the first thing that you're stuck with trying to learn is how to program. Okay. The fact that it's an object-oriented programming language kind of gets, or can easily get, a bit lost in the noise, because going from zero to writing small programs is a big task. It's hard, it's complex, you've got to learn a bunch of new stuff, and it's very, very easy to lose sight of the bigger picture of why are we doing it in this particular way. But the more, or not the more, the better understanding of the fundamental design principles of the language that you're learning you have, that was an impressive sentence, to some degree, the easier it is to learn it, right? Because if you know what the designers were thinking when they were building the language, then you can make reasonable guesses about what it is the things that you're doing mean. Like, why are you doing it that way? If you have something relatively unknown, you can make reasonable predictions about how it's going to function. So, having said that, let's start talking about object-oriented programming. So object-oriented programming is actually almost as old as what I would call modern programming. So the first not exactly definitions, but the first attempts to introduce the idea of object-oriented programming happened way back at the end of the 50s. So at that point, we hadn't even had digital computers for very long, and certainly hadn't had stored program computers for very long. Like the first stored program computer, that is one which has some way of representing the program that is separate to the physical structure of the computer, were only created basically during World War II, so 39 to 45. I think Zeus's Z3 actually came out in 38. But the Bletchley-Park Colossus was only built in 42, I think, or thereabouts. And of course it was a secret until the 90s, so no one knew. And things like ENIAC were only built like just after the war. So to go from that World War II technology of little, round cathode ray displays which could barely do anything, and plug boards, to what effectively, although they were relatively speaking very underpowered to modern computers, effectively a modern computer by the end of the 50s, is a massive step. And to go from writing programs by literally flipping switches to having something that is, again, not as neat and powerful as what we have now, but relatively speaking, basically the same idea. I mean, punch cards look archaic and funny, but you're still essentially writing something on some version of a piece of paper. It's just now we have a keyboard and a digital piece of paper. To do that in basically 10 years is a huge step, and even at that point they were thinking about things like object-oriented programming. So where do I want to go from there? So the ideas of object-oriented programming have been floating around for a long time. It didn't really reach sort of what I would call public usage, so interest outside of academic circles, I guess, until the end of the 70s. So it took about 20 years before the ideas that people were coming up with in the 50s were coherent enough, and we had computers that were powerful enough to efficiently implement them. Took about 20 years. I think I doubled back on the sentence there. Anyway, because one of the things about object-oriented programming is that it adds a certain amount of overhead. So in this beautiful diagram that I've created just for Nick here, each of these objects might store a number. Alright. But they also have all this other overhead here. So they've got some kind of memory structure which says that these are each an object. They each have something that indicates they belong to this class somehow. They've got their own memory address. They might store further information, which then requires other memory addresses and all sorts of things. So if you're working in the 60s or the 70s and you're dealing with things like, I don't know, drum memory or other nonsense like that, and the memory is outrageously expensive and you don't have much of it, then doing something like this is not really feasible. It's not cheap, right? So it's much simpler if we just have, instead of a definition of a class that we have to store in the working program, and then each object which has some idea of the little box that it's in and some reference back to that class, and then somewhere to store the data. it's much simpler to just have a piece of memory, so 4 registers which store the data. Well, that's meant to be a 5, isn't it? And then as a clever programmer, you just kind of remember where the data is, and what you want to do with it is hard-coded into the program, essentially. And you don't even have that much space to fit a program in, so you can't even really write big programs, at least not conveniently. Certainly in the 60s and 70s, when sort of you have this split between mainframe computing and microcomputing developing, where microcomputing, you have like a very limited amount of memory to build a program in. Mainframe computing, of course, you can have a stack of cards as big as you want, but those cards are actually, you know, if you think of them in terms of bandwidth, they're pretty low bandwidth, right? Because you've got a physical piece of paper this big that stores, you know, a fair number of bits, but it's not a lot. You know, you can store like a 50 element array, which is fine, but it's not great, as long as all your numbers are 10 or less. So it of course depends on your punch card regime about how that works, but you know, that's still not a lot of data that you can store on a single card, and there's sort of only so many cards you can fit into a physical space this big, or you know, twice that or whatever, as compared to what we can do today, where we have in effect unlimited memory. Right? It's not that you can't do something that will cause modern computers to run out of memory, but for any practical application, well, not any practical application, for like 99% of practical applications, we've got better hardware than we really need. Like vastly better hardware. So that shift in hardware kind of happens somewhere about the 80s, where it starts to get free enough that you have coming down from the mainframe level of computing enough memory to write structurally more complicated programs than horrific bundles of assembly and C code with go-tos everywhere, because you absolutely need to save every single piece of memory. So about that time, we start to see our first usable object-oriented languages. So you get Smalltalk, which claims it's the first object-oriented language, but it isn't. I can't remember what the first one is, but Smalltalk shouts about it a lot. But more importantly, in 1978, spanning to about 83, you get C++. So C had embedded itself in the programming world because it's what Unix was written in. It worked on most sort of mainframe computers and microcomputers at that point. There was a compiler for it. It was relatively high level compared to writing in assembly code. It was quite portable because there are lots of compilers for it. And it had just enough power to be useful, but it was close enough to the system that you could still write the programs that you needed to write. But then you get Bjarne Stroustrup saying, well, I've heard about this object-oriented idea and I like C to some degree, but I would like more control. And this is where we start to get the practical implementation of object-oriented programming in reality. That said, the ideas that he used in building C++, again, this is not to imply C++ is the first object-oriented programming language ever. That, like, the first one was actually made, you know, back in 58. Like, technically Lisp has certain levels of object orientation in it, but it's kind of the first one where it becomes a mainstream programming discipline. So the ideas that he was bringing into that was not just this idea of, well, if I have these object things, I can collect data and methods together. It's ideas about how to build large complex programs. And that's really what object-oriented programming is about. It's not about sticking stuff in boxes. It's about control and structure and clearly delineating what things mean so that you can separate things sensibly and reuse them. So the idea of an object is not just this box that contains data, it's a structure which controls access, is really the important part of it. So the classic picture of this, so it still revolves around the data ultimately, but the classic picture of this is this circle model thing, where an object, see if I can draw a better circle. An object, regardless of whether you're using a class-based object-oriented programming language or not. So there are other ways of doing object-oriented programming than what we see in this subject, particularly class-based and message passing. So Smalltalk is a message passing one. JavaScript is a prototype-based object-oriented language, or at least used to be. So they're the three main ones. So it doesn't matter which one of those you use. So here in Java and C++ and languages like it, it's class-based. That's by far the dominant paradigm. You can decide whether you think that's a good idea or not, but it seems to be the one that works pretty well. But all of them have this basic idea, right? Because data is sort of the most sensitive part of the program, because the program kind of only works if your data is, well, I'm about to make essentially a trivial, stupid statement, but let's see if I can make it make proper sense. If you allow anyone access to your data and they can change it as they wish, those changes are not transparent and not recorded. So if you don't know those changes have happened and you're expecting the data to be in a certain state, you don't have a way of really verifying that or guaranteeing that if anyone can touch the data. So one of the core ideas in object-oriented programming is that data is not just not just carried around by objects, but is protected by objects. And that the access and control is mediated, mediated by methods. Because if you don't do that and you don't hide your data, Nick will steal it. I've seen him on a camera at his house. He's got a huge pile of everyone's data just sitting there. He's not even doing anything with it. But the non-silly version of that is, if you don't protect your data, some either malicious or incompetent programmer, which may also be you, will come in and do something to that data that they shouldn't be doing. So you can think of sort of obvious malicious ones. You know, if you have, going back to our bank account example, if everyone can access the balance of the bank account, then that money's not going to stay in there very long, right? Or it's going to suddenly get very, very large. But there are more serious and more insidious ones, because that one is protected through access security, right? Like, you know, physical and electronic access security, not in terms of the programming language. There are more serious ones. So if you've got, for example, a piece of medical equipment that is relying on coordinates to deliver a medical treatment, say like a radiography machine, so it is literally shooting someone with hard radiation. If if your programming team just has the data sitting there and doesn't coordinate about how that data is represented and how to access it, things can go very, very badly. Similarly, you could at least roughly imagine a problem with something like designing critical system software. I mean, not that radiology machines aren't critical system software, but guidance systems on a plane. So if you've got an autopilot, piece of autopilot software, and then you've got control software that the pilot runs, and then you've got software from some kind of mission planning system, if the way they interact with the data is not coherent and doesn't match up, then you get planes that decide a good place to park is the side of a mountain. And most people are not too happy with that. So one of the principal ideas then of object-oriented programming is not exactly to prevent that completely, because you can't prevent it completely. If you've got a rogue programmer and they've got access to the source code, then, they can just change what they want. But the idea is to allow sensible programmers to delineate the boundaries of how the data is accessed. And within the expectation that other people are also going to be relatively sensible, control the access to it. So this is called encapsulation, and is really probably the most direct founding principle of object-oriented programming. The data should be encapsulated in objects, because that allows you that extra level of control that says maybe you stop people from changing that data. Right? So there's no way that a non-malicious but incompetent programmer can modify that, because I guess you probably haven't seen this one before, but like if you mark a variable final in Java and you try and change its value, you get an error. And why am I doing that? Where is my... No, not that one. That one. Let's go to the workspace. So because the data is inside the method, I have a number of ways now of controlling access to that data. Or even better, let's not even have that at all. So I can create a class that has some piece of data in there, and hopefully you can already see that I can set that data at construction time using the constructor, but that's all I can ever do with it. So this is a very extreme example, of course, but there's absolutely no way that I can, as a non-malicious programmer, so if I was malicious and I had access to this, of course I can add something that allows me to change it. But all being well, and people are not trying to deliberately mess things up, there's no way I can accidentally mess up this value, right? So there's no way by writing another piece of code I can not have the value that I passed in to begin with. So this bit works fine. You know, it creates it and prints it out, but I can't access that data. I can't change that data. So the fact that this data is encapsulated in here, so the object, well, the definition of the class hidden means that the int data is encapsulated by its object, means that I now have control over that piece of data. At least some level of control. So when that data is sensitive to change, so not just sensitive from a security point of view, so, you know, names, addresses, phone numbers kind of thing, I mean, literally, if you change it, you might ruin the functioning of the program, that is now basically prevented by this idea of encapsulation. This idea of encapsulation also has the nice side effect that objects carry around data and methods together. Right, so I can pass, I mean, it's not really the variable h, but I can pass the object that the variable h references around to other places, and they all get the same thing, so it doesn't change unexpectedly. But the primary goal here is that the int data is protected. So it's inside this inner circle in here, and it's only through the methods that I have access to it, and thus by defining only the methods that allow the types of access that I want in terms of system design, so by doing that, I stop data from being modified in unexpected or unintended or dangerous or bad ways. So the other side effect of this is now that the class / object is a structural thing, a structural entity, I guess I want to say. Didn't run out of tea, I just had to fill the cup. So how am I going to phrase what I want to talk about here? So imagine we're out here as the classic eyeball looking in from our physics textbook with scary black eyes, nice eyelashes. Oop. Why am I using the mouse? I can write badly much faster with the pen. And I'm looking at an object. What do I see? Do both eyes? Oh, geez. Well, it's I don't know. I can kind of do the nose, right? And the eyelashes are the other side. So, obviously, I don't mean literally looking at an object here. What I'm in a silly manner referring to is the rest of the system outside the object. How does it see the object? All right, so we've got, this is what our object thinks it looks like. So the object has this information, it's got data, it knows what its methods are and stuff like that. What does it look like to the rest of the system? What's the external perspective? Exactly, thank you, Nick. Well, the external perspective of the system is only, in Java terms, is only the public components of the object. So the rest of the system only sees exactly what you expose. So as far as the rest of, so this is a side effect of encapsulation, but as far as the rest of the system is concerned, what does it mean to be an object of whatever type this object is? It's that it has those public components. It doesn't care about what's inside it. So the rest of the system doesn't know that data is inside here, and it, even better, it doesn't care. So the rest of the system doesn't need to know about the inside of the object. It's only that outside external interface. So that's the actual name of it. It's only the external interface that really defines what the object is and what it looks like. And this is our first step in the principle of abstraction. So abstraction is the object-oriented principle that not only does the system not need to know what's inside the object, or doesn't know what's inside the object, it shouldn't know what's inside the object. That's not important. All the system needs to know about is what this public interface looks like. So the idea of the object as a thing inside the system is abstracted to that public interface. The implementation is not irrelevant to the functioning, but it is irrelevant to the functioning between the components of the system. There probably is a thing where I can type text, but I don't know where it is. So this is So this is maybe not the order that they're normally presented in, but where's my right diagram? But sort of working naturally from the idea of objects, our first principle is that of encapsulation, that objects hide data and it's protected by methods. Once you've got some way of doing encapsulation, you've got a way of doing abstraction. So what abstraction means is that we can hide the implementation details. Yeah, so I can quite happily do... That works fine, but yeah. So if all you want to do is work with, like, you know, let me, before I get too far on that, let me rephrase it another way. Imagine you're working in a group programming a piece of software, and you say, okay, you're going to go over and do section A, you're going to go over and do section B, and you're going to go and do section C. What do you really need to know about section A and section B and section C if you're working in one of the other three? So hopefully you want to reduce it to as little as possible. So you want, if you're working on section C, all you really want to know about section A, assuming that they're well defined and reasonably separated, that your team leader has done a good job of splitting the jobs up, is how to talk to it, how to interact with it. You don't care what that team is actually doing to implement it. All that stuff is hidden away. You don't need to know about it. It should be abstracted. Oh, let me move my face. Where's Ops gone? Okay. Now that's actually readable. Yeah. So that very idea of reducing the amount of information that you require to or not to understand necessarily, but to be able to use the thing that you're interested in, is essentially the principle of abstraction. So even if it's not objects, things in an object-oriented programming language should only expose publicly not exactly the minimum, but the abstracted details of what's necessary to know to use them. So if I do something like if I write a method to calculate Fibonacci numbers, and you want to use it, what do you need to know about it? Is it this bit? Is it anything else there? if I hit T, does it change to the text tool? I don't know. The way I'm accidentally changing it is hitting the middle mouse button on the stylus. Because I'm in Linux, that'll do a paste, so it just pastes whatever I've selected before. So if I've got this Fibonacci method, and I'm over here in Runner, so let's make this static, because I don't want to confuse the matter too much. What do I need to actually call it? What do I need to use this thing? Well, not all that much, right? I need to know its name. I need to know what information I have to give it, the parameters, or the arguments of the parameters to give the proper name. And I need to know something about what comes back out of it so that I can process it appropriately. So, as far as the outside world is concerned, everything that they need to know about this Fibonacci method is that it returns an int and that it takes in an int. So there's some other technical details as well, like, you need to know it's static to be able to use it properly. You need to know what the name is. But really, just in general terms, the important part is, from the outside, is what goes in, what comes out. This bit, as far as the outside world is concerned, is irrelevant. I don't need to know that Fibonacci does it through this recursive approach. Right? It could do it a completely different way. So thanks, Nick. Is the fifth Fibonacci number really 5? That doesn't seem right. 0, 1, 1, 2, 3. Oh, it is. There you go. That was unexpected. Let's do Fibonacci 10, just to make a difference from the other one. There we go. So to use it, I don't care what's over here. Right. Makes no difference to me whatsoever. So I could do a completely different one. So I can change this and say, no, I don't want that. I want a equals 0. I'll probably get the details of this wrong, but it's not really important right now. So I'm doing a rather bad one here. That'll probably work. So, regardless of whether I got the technical code there right to begin with, I happen to, whether I got the code there right anyway, this bit doesn't change. And that's a really important observation for object-oriented programming, and that is the basis of the principle of abstraction. That once you have encapsulation, if you don't change the fundamental design of a class or object, or however you want to think of it, the way you interact with it shouldn't change. So if I declare that the very idea of hidden dictates that it should have a Fibonacci method that takes an int and returns an int, that should be part of its abstract definition, but the way that it's achieved is not part of that. Okay. Not part of that at all. It's not relevant to the rest of the code how that's achieved. So you can see there was absolutely no change whatsoever here. I literally changed none of the code at the point that it was used. So there's, a good, 11 different sensible ways to calculate Fibonacci numbers. Doesn't matter which one's behind this method. This piece of code does not care, and nor should it have to. And again, that's the principle of abstraction. That I don't have to care what is behind the names. As long as it works properly, all I need to know is what do I need to give you to make it work, and what do you give back when you're done. So this principle of abstraction extends even further, right? So once you start thinking along those lines, the principle of abstraction starts to help us design, at least at a basic level, how to build these classes. Because if you're thinking about, well, let's think of it in terms of the code as not exactly as it's running, but as it's going through. If I'm the main method of this class and I want to get the 10th Fibonacci number, what options do I have? So I could do it myself. So I could write extra code to do it. I could find it written somewhere else and call that. Or if it were a more complex process, I could break it down into smaller steps and do all of those. So Fibonacci is not a great example of that particular thing. But which is the most sensible? Well, if it's already implemented, I shouldn't be doing it again myself. So unless the thing that I want to do is the actual function of this piece of code that we're writing here, that function should be somewhere else, and it should be, in a more broad sense of the word, encapsulated. So I shouldn't be writing the code to calculate the Fibonacci numbers here. That is not the job of this method. The job of this method is to run the program. If part of running that program is to calculate a Fibonacci number, then there should be a different method whose precise job it is to do that thing. If that job requires it to do other jobs, there should be other methods to do that. But from the perspective of this piece of code, it again doesn't care, nor should it have to. Because if it takes 50 different steps to create a Fibonacci number, we shouldn't have to write those out here, just as in exactly the same way that we shouldn't have to write out the actual code to compute a Fibonacci number. We should be able to just say, give me the Fibonacci number, and the problem of computing that is then the problem solved by this Fibonacci method. Maybe it calls other methods, maybe it has to do other things first. That's absolutely fine, but the point is that at this level you don't know and you don't care. and you don't want to care. So how does this help us in building systems? Well, this means that we can do things like define an interface. So there is the, what can I define? Sorry, I'm trying to think of a non-boring thing that has an interface. Actually, no, let's use the assignment, because you can do this as an interface. But I'm going to call it my list. So Java has a specific programming structure, so you don't need that. We do have lessons on this, but you don't need to learn these for this particular subject. Knowing that they exist is handy, but you'll not be assessed on this part. But Java has a specific structure for building abstract definitions, which is called an interface. So it's a place where you can write down what it means to be one of these. So if you want to be a list as I define it, then I want to be able to, so I'm going to introduce another thing. So these are generics, just to make, so don't worry about what the generic is, that's really not important. I just want to make sure the linter doesn't whinge at me. But I want to be able to add something to my list. So this should look somewhat, I want to be able to maybe add a position. I want to be able to make noise like other animals should. I want to be able to retrieve an element at a particular position. I want to be able to say what my size is. Yeah, so there's a, maybe I want to be able to reverse the list. Maybe I want to be able to sort the list. So as Nick is filling out some other variously interesting or amusing ones, yeah, you can see that what we're defining here is the idea of being a list. It doesn't tell you anything about how it's going to do that. So if you think about this, for those who've started the assignment, if you think about this in terms of the linked list that you're building, anyone outside your linked list class doesn't need to know that it's a linked list. Right? They don't need to know that you've got a node class inside it that has a reference to another node, and that you've got a variable inside your linked list that's probably called head that says that there is a node here, and that you've got an int that stores the size if that's how you're doing it. And all sorts of other things. All you need to know from the outside is that these things exist. Right? That's what it means to be a list. That doesn't return a list, Nick. You can eat the burger. It's alright, we can't hear you. So this is precisely the idea of abstraction. So this my list thing is the abstract definition of what it means to be a my list. So it has ways of doing these things, but we don't have to know about it. Then someone can go and implement one And inside that, they can then have well, however it is they're going to do it. Alright. So the actual implementation may work a number of different ways. So you can look at this MyList definition and say, okay, if I create one of these, then I'm going to be able to add to it. I'm going to be able to add at a particular position. I'm going to be able to retrieve things, get the size, reverse it, sort it, check if it's empty, append something and get probably a copy of the list, stick something at the front. I can get it to eat a burger. How that happens inside a particular implementation is then no concern of the rest of the code. So the fact that maybe it's implemented by having an array of elements, or maybe it's implemented by just using Java's array list. Doesn't matter. Not relevant anymore. If someone's using a MyList, they don't need to care about what's in here. So this, I don't know about neatly, but this leads us on to our next object-oriented principle. In fact, it leads us on to two of them. Which way around will I do it? So what do we got? 20 minutes. So the last two are a bit more complicated in a certain way. But now we've got this idea of abstraction and this idea of encapsulation. And say we've got can I don't think I've hidden all the tools to make it cleaner, and now I've ruined everything. Or I can't do the trickier things that I want to do. So now, say we've got two objects sitting in our system and they look exactly the same. Alright, so they've both got 3 red spikes and blue spots. Okay. But inside them, it's hard to draw the inside, but inside them they may be different, but externally they look exactly the same. So what we want is to be able to treat these things the same. So from stepping from encapsulation to abstraction, we've got this mechanism where we can hide the internal details of stuff, and from the outside all we care about is the abstracted external interface. Sort of everything's a black box of varying shades of black, which means we want the idea of polymorphism. Things that look the same should be able to be used the same. Or, to put it another way, sort of the inverse of that. So polymorphism literally means many shapes, is that any given thing, depending on which external interface it chooses to expose, if it's got a choice of several ones, should be able to be treated as one of those. So in Java, no, let's not do that. So, have we got, yeah. So as an example of polymorphism there, we have this interface mylist, and we have the myArrayList implementation. So you can see it implements mylist. Again, this is not part of this subject, so you don't have to worry about the exact sort of programming connotations of that. But basically what this is saying is that myArrayList is also a mylist. It exhibits that type, so it should have all of these methods. But there's also a myNickList, right? So it is also a mylist, and it has like once it's complete, it has all the same methods. So the myArrayList and the myNickList can both be treated as mylists. They can also be treated as a myArrayList or a myNickList. So a myNickList has an array list of elements. It also has a banana. And if you ask its size, it returns a banana, as you would expect. But externally, if it chooses to do so, it looks exactly like a mylist. It may add other stuff as well. So a myNickList may have a method that is not on the mylist list of methods. All it says is that I guarantee that you can treat me this way if you want to. Feels like a creepy sentence to say, but that's how abstraction and polymorphism works. So for example, the myNickList has an eatBanana method. That is not part of the mylist method, the mylist definition, right? And it's not in the myArrayList, apart from the fact that myArrayList is nowhere near complete. There's no idea of a banana in there. So the myNickList builds on the mylist and says, I also have a banana. So as someone pointed out, never heard someone say list that many times in a sentence. So we have a myNickList myArrayList and the idea of a myList. So we can treat myArrayList or myNickList as a myList. And that is essentially the principle of polymorphism. That myArrayList or myNickList both say that they have their normal type, which is myArrayList or myNickList, but they also have their type of myList. So it can be treated in different ways. MyList is also an object. Where's my thing? So there is actually a class called object. So myNickList and myArrayList can be treated as a myList because they look like a myList. And myList can be treated as object, which means myArrayList and myNickList can also be treated as an object, because they look like an object, they exhibit that shape. So each of these has many shapes, as polymorphism says. And this is not the only way that polymorphism is exhibited. We've actually seen it occur in a couple of different ways already. So polymorphism is a more general principle than just object-oriented programming, than just a principle of object-oriented programming. It's just that object-oriented programming says you have to have polymorphism. But we've seen functional polymorphism, or ad hoc polymorphism, I guess is the normal name. So that's where you have two methods which have the same name but different parameters. Right? So it's where another way of looking at polymorphism is if you've got something with the same name, but it can do different things depending on how you treat it. So what I'm outlining here is the key polymorphism in object-oriented programming is that of type polymorphism. Right? So that a single object can exhibit multiple types. So how do we achieve, in our last 10 minutes, how do we achieve this polymorphism? Or what is one aspect of being able to achieve this polymorphism? So the last of the four pillars of object-oriented programming is in some ways the inverse of type polymorphism. But also the way that it's achieved. Actually, strictly speaking, I drew that definition the wrong way. In Java terms, this is in fact the way that it happens. Sort of. I'm going to redo it the other way. Let's lie a bit to make the picture clearer. So it's all well and good being able to say that if I've got a thing that exhibits multiple types, then I should be able to treat it as any one of them. But the inverse of that is that if I've got a thing that has multiple types, it should receive the properties of those types. So that is that if I say a myArrayList is a MyList, then it should get all the, somehow, there are different ways of achieving this, but it should get somehow all the things that a MyList has. And this is called the principle of inheritance. And it's like an is a relationship. So myArrayList is a MyList. And MyList is an object. Yeah. So unlike inheritance in the real world, either genetic or financial, in object-oriented programming languages, you have some notion of a relationship of a child and a parent, and the child gets everything the parent has. So do I have a an example? So the interfaces work well enough here. So a myNickList is a MyList, and it is also fruity. myArrayList is just a MyList. So whatever MyList has, both myArrayList and myNickList get all of those things. In particular, they have all of these methods. So you've got kind of, this is why I say it's kind of like the inverse of polymorphism. So in Java, you set up these inheritance structures, and that forces the information to be passed down, if you think of it going parent to child, top to bottom. But that allows type polymorphism, because if you've got everything that the parent has, you can be treated in the way that the parent is. Okay. So myNickList can be treated as a MyList and can be treated as fruity because it receives everything that a MyList has. So it's got the methods size, add, add at, get. Because it's fruity, it also has the method eatBanana. Independently, it has the doTheNick method. So it can define its own things on top of what it gets from the parent. But because myNickList is a MyList and it is also fruity, it gets all of those things. So sorry, there's a commenting thing. I think a good diagram for inheritance would be sets in maths. Sets actually more correspond to type information. Like if you think of sets and subsets. Yeah, it is kind of similar. Like it's not completely identical because it's so if you think of the sets like this, you've got parent set. Oh, that's the wrong way around. Woo. You've got the parent set, but the child set is bigger, which is kind of the inverse of the way you'd think of it in set theory. So in set theory, there's no parent and child thing to begin with, so it doesn't matter. But a set derived from another one would normally be a subset, I guess. I guess that's not true. But if that helps, you can think of it that way, that the child, you've got a parent set of things, and a child set contains all of those parent things plus whatever else the child adds. So if the child has a child, you can think of the original parent as a grandparent. It's not unheard of to call it a grandparent. Often parent's parent is the name. Okay. So, just to wrap that up, now that we're at the end of the lecture, object-oriented programming, to a relatively high degree of agreement, so people will always argue about what the most important things are and what you do and don't need. But object-oriented programming, and to make an object-oriented programming language, you need something that can implement these 4 principles. By far the most important of the 2 are encapsulation, that you can hide data and protect it by methods. So data should be hidden in objects and access controlled through methods. And abstraction, that outside of a particular piece of code, you shouldn't have to care about what the inside of that particular piece of code is. In particular in object-oriented programming, that when you're outside an object, you don't need to know what's going on on the inside of it. All you care about, and effectively the definitional notion of that object, is the external interface, the public components of it. Everything else on the inside is implementation details and not important. So between those 2, you've got your major principles of object-oriented programming. So you can almost get away without the other 2, but not really. But they also kind of naturally lead to the idea of polymorphism, that you start defining public interfaces and you have different implementations of them. So I've got Nick's list and my my Nick list and the my array list, and externally they look exactly the same. Then I should be able to kind of treat them the same. So the flip side of that is that any given thing, as long as it obeys the contract of what a certain type is, should be able to exhibit that type. So a my array list obeys the contract of being a my array list. It also obeys the contract of being a my list. It obeys the contract of being an object. So it should be able to exhibit those 3 types. Or to flip it around, it should be able to be treated as any one of those 3 types. A my Nick list also is fruity, so it should be able to be treated as at least 4 different types. And that also somewhat naturally leads to the idea of inheritance. That if I say this type is a subtype of the other one, it should get everything from that parent type. So a child type should not have less information than the parent type does. This is also the mechanism that helps us to implement type polymorphism. So I think we'll wrap that up there, because we're at we're out of time now. So in a way, what I wanted to do with this lecture was obviously introduce you to the 4 pillars of object-oriented programming, but get you to start thinking about that in terms of the exercises that you're doing. So when you're doing the bank account 001 or the summer 001 or the assignment, think about, why does the node class have a private node as a data member, and why does the linked list have a private node as a head as the data member, but its methods, are just add or remove or whatever they are. And how does that fit into the object-oriented structure that was set up? Because you could write a functional linked list where basically everything is public, and you can just hook and unhook the links yourself, which was the traditional way of doing it because there was no idea of private stuff. But if you think about it in object-oriented terms, that structure of having a node class that keeps track of what the next one is and keeps track of its data and sort of limits access to that data, and then having a linked list class which has inside it a node which hooks up to other nodes but doesn't let the outside world either know about that or directly access that. Where was I going with that? That's all set up in an object-oriented fashion. So then, in principle, for everyone who actually completes the assignment, regardless of how you completed it, if I was using the code of one student who completed it, I could swap it for the code of another who completed it, and my program wouldn't know the difference. So out of these four principles of encapsulation, abstraction, inheritance, and polymorphism, I get neatly separated, modular, reusable code. That's where this whole object-oriented thing is leading. And once you have neatly separated, modular, reusable code, building large systems suddenly becomes a much simpler prospect. So going back to our Team A, Team B, and Team C weak example, if Team A is working on their bit and it's all nicely separated, we don't need to care what they're doing. We can write our bit and they will, within some degree of precision, work together when we stick them together. So all of a sudden this project that takes 3 teams to work it on becomes 3 semi-independent projects that are smaller and simpler, and then you can break those down further. Alright, let's leave that there because some of you have to rush off to labs and some of you are starving hungry. Thank you all for coming out. As usual, share, like, and subscribe. Thank you again to Raid Shadow Legends for totally not stealing everyone's data. It's free to play, so obviously they're making money somehow. It's just through goodwill, right? You make that much money on microtransactions. Yeah, thank you for NordVPN for sponsoring the mid-reel break as well. And keeping our data secure and not having any breaches ever. Yeah, actually, seriously, if someone from T2 somehow is watching this, I will take a sponsorship from T2. Programming Fundamentals brought to you by T2. Or the T-Center. T-Center is also good. This is not a diss on any other T-shop. It's just that T2 is well accessible and convenient. Alright, so let's leave that there. Thank you everyone again for coming out. Have fun with your assignment. Again, those who don't know the assignment is out. You might want to take a look at it. I don't expect you to complete it instantly, but it will take some thinking and a little bit of time, but you should, if you start now, have plenty of time to do it in. Alright, I need to get home and move some bookcases, so I will stop there. Thank you all. Bye. Bye, 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 bye.